Okay, let's look at this problem set number 26. We've gone back into chapter 7 to pick up this problem dealing with power. And these are just some energy problems that were old exam problems that will be useful in getting ready for the exam. Um, let's start with this problem 36. You have a surface here and a block of dry ice. Now you remember dry ice sublimes and creates a layer of gas underneath it so that it can float on the surface without any friction. And you're pushing on that with the lobster hand. And if that dry ice were all by itself, it'd just speed up and go faster and faster. But it's got an anchor. It's tied by a massless string to a brick. Okay? And we're told that the brick has a mass of 10 kilograms and the dry ice has a mass of 20 kilograms. And we're told that the hand is pushing such that we have a constant 10 meter per second velocity. Now, remember from back in the day, whenever we see a constant velocity, we immediately translate that to acceleration zero or equilibrium. Things are in balance. Now, if I draw a free body diagram for the brick, I have a weight force on the brick, and I know that's 100 newtons. I have a normal force by the table on the brick. I know that's 100 newtons. I've got a friction force. It's kinetic friction because I can hear the scraping going on by the table on the brick. And then I have this tension force by the string on the brick. If I draw a free body diagram for the dry ice, I have a weight force on the dry ice, and that's going to be 200 newtons. I have a normal force by the table on the dry ice. That's also going to be 200 newtons. I don't have any friction on the dry ice because it's floating on that layer of gas, but I do have this tension force by the string on the dry ice. And then, of course, the normal force of the hand on the dry ice. Now, the first part of this problem is asking us to find the power delivered by the hand. Now, you know, whenever something's moving at a constant velocity, that we can write the power as that force times that velocity. Well, where does that come from? Let's go back a little bit. Power is just how much work you can do divided by how much time it takes, how many seconds it takes. Well, I can write the work as the force times the distance, and then I've got to divide by the time. Well, the distance or the displacement over the time is just the velocity, okay? Now, the velocity is given, that's 10 meters per second. So I need to know, in this case, since we're looking for the power by the hand, the force would be the normal force by the hand on the dry ice. Now, how am I going to find that force there? Well, I'm going to find that force there by working backwards. I know that this is the easy kind of friction, that's just the mu sub k times the normal force. And we're given that this rough surface has a mu sub k of 0.75. So this is going to be 0.75 or 75% of 100. So that makes that 75 newtons. Well, this diagram has to scream zero acceleration or balance. So that means this tension force must also be 75 newtons. Well, this is the other end of a massless string. We know that on a massless string, by Newton's second law, the pull has to be the same at both ends. So that's 75 newtons. Again, the free body diagram for the dry ice has to scream balance. So that means the normal force is going to be 75 newtons. So now I can go over here and say that I've got 75 newtons times 10 meters per second, and that's going to be 750. A newton meter is a joule, and a joule per second is a watt. So this is going to be 750 watts. Now, the second part of this problem says the hand stops pushing. And you know that things want to keep on going forever, that's inertia. But it's got this anchor dragging behind here with this friction force that's constantly bleeding energy out of the system. And in part B, we want to figure out how far does this go before it stops. Now, because these are moving together, the dry ice and the brick, I can treat them as one unit, as one thing. And the initial kinetic energy of that one thing is going to be 1/2 times the mass total, which is the mass of the brick plus the mass of the dry ice, times the speed that they're going squared. Well, that's going to be 1/2 times 30 kilograms times 10 meters per second squared. That's going to be, that's 100 times 30 would be 3,000, so there's going to be 1,500 joules. So if I use my energy initial plus Verk is equal to energy final, I start with 1,500 joules. This friction force here is doing negative Verk, 75 newtons times the displacement, how far it scrapes, and then it comes to a halt. When I solve that for delta x, I get 20 meters. Okay. Now, folks, we're halfway done because problem 41 is worked in all its gory detail in Monday's lecture. And this is the homework that's due Monday, so it's going to, if you're just patient and watch that lecture like you're supposed to, it will have the solution to that problem worked out in all its gory detail. So all we need to do now is look at problem 40. Okay. Again, I leave that up longer, but I realize that you can just pause the video and make time stand still. Problem 40 is a creative one. I'm quite proud of it. We got this carnival ride, amusement park ride, where we start out at one level, and then we jump up 2 meters, and then we come and have a loop-de-loop, And you know what? I just haven't given myself enough room for this ride. Let's try it again. So we start out at a level, we go up 2 meters, we go around a loop-to-loop, and then up, and actually we just launch we start out with a spring, and we launch this car that's got 2 riders in it, okay? And the spring constant is big, 30,000 newtons per meter, and we compress this thing by 2 meters to get it started. And then it goes zipping up this frictionless track. Remember, if I don't have hash marks, I assume it's frictionless. Well, there is friction here, and that region lasts for 2.5 meters. And we don't know the coefficient of kinetic friction. We do know that the radius of this loop-to-loop is 4 meters, so you can see that this may not be entirely drawn to scale. And we're going to call this starting point A. We're going to call this point at the top of the loop-to-loop B. And then what happens is the cart goes around the loop-to-loop and then launches up here and then falls back down. So if I call the lowest point in the problem my h equals 0, then this level here would be h equals 2 meters, and this level here would be h equal 10 meters, right? Because that's 4 and that's 4 and that's 2. And we want to know at the end of this problem how high they get at this point C, which is a turnaround point where they fall back to earth and demand their money back. We're told that the mass of the car plus the 2 riders is 250 kilograms. If the speed of the car is 12 meters per second, we want in part A to find the coefficient of kinetic friction. So for A, we want to find mu sub k. Well, this is not a collision, and it's not about time, so that means it's an energy problem. So I start with the grand high energy initial is equal to energy final, except when it's not, and it's not when there's Verk done by an external agent. Now, I want to know something about this Verk. I want to know what the coefficient of kinetic friction is in that region there. So I want my initial event to be on one side of the Verk and my final event to be on the other side of the Verk. And I want these to be events where I know everything about the energy, because this is the part I don't know. Well, I know everything about the energy at A, and I know everything about the energy at B. So those will be my initial and final events. Now, at each of these points, I ask the same 3 questions I always ask. First question, is anything with mass moving at A? Not yet. Second question, is anything up off the floor, or what I'm calling the floor? No, not yet. Third question, are any springs stretched or compressed? Well, yeah. So I have spring energy at A. And then the Verk is going to be done by the friction force. It's going to be negative Verk, bleeding energy out of the system, times that distance of 2.5 meters. Then we go to B and we ask the same three questions. Is anything with mass moving? Well, yeah, we're going at 12 meters per second up there. So there's kinetic energy at B. Second question, is anything up off the floor, what we're calling the floor? Well, yeah, there's gravitational potential energy at B. And the third question is, are any springs stretched or compressed at B? No, not anymore. It was compressed at A, but not at B. So this is what we need to plug in here. And you can see that the potential energy for the spring is 1/2 times 30,000 newtons per meter. It was compressed by 2 meters. I've got to square that. The friction force is going to be mu sub k times the normal force. Well, this is a flat section of the track, so a free body diagram is going to have a weight force of 2,500 newtons and a normal force also of 2,500 newtons. And then this friction force, which is going to be mu sub k times the normal force. So the normal force is going to be 2,500 newtons. The distance, this delta x here, is going to be 2.5 meters. Well, that's going to equal the kinetic energy at B, which is 1/2 times 250 kilograms times 12 meters per second squared. And then the gravitational energy is going to be the mass, 250 kilograms, times G, which is 10 newtons for each kilogram on Earth. And then the height. Well, this is what we're calling height 0. That's 2 meters there. That's 4 meters there. And that's another 4 meters. So I got 4 plus 4 plus 2 meters. That's going to be 10 meters. Now, folks, that may look ugly, but it's just algebra. There's only one unknown there. All of these things are numbers. This is going to be 60,000 joules minus mu sub k times 2,500 newtons times 2.5 meters is equal to, let's see, this is going to be 25, is it really? 25,000 joules plus, oh no, that's the 25,000 joules there. This is going to be 18,000 joules, and this is going to be 25,000 joules. Okay, so when I solve that for mu sub k, I'm not going to drag you through the algebra, but we get a fairly steep 2.72. And remember, our mu sub k values are pure numbers. They don't have any units. Well, that's part A. Part B asks us to find the normal force, magnitude, and direction exerted by the track and the cart at point B. Well, since the cart's going in a circle there, it's going to have centripetal acceleration, and that acceleration, of course, centripetal means center seeking, and that's going to be v squared over r. Well, that's going to be 12 meters per second squared divided by 4 meters, and that's going to give me 36 meters per second squared down. Now, if I draw a free body diagram, let's draw a free body diagram for that cart. I'm going to have a weight force on that cart of 2,500 newtons, and then I'm going to have this normal force by the track on the cart. Well, that's what I'm looking for right there. Well, my diagram should scream down because my acceleration is down. But how loud should it scream? That's always given by F net equals MA. If I call down the positive y direction, then my F net is just going to be my weight force of 2,500 newtons. That's down, so it's positive. I've got the normal force by the track on the cart, that's down, so it's positive. That's going to be 250 kilograms, the mass, times the acceleration, which we said was 36 meters per second squared. And since it's down, it would be positive. And if I solve that for the normal by the track on the cart, I end up with 6,500 newtons. Now, part C asks us to find this maximum height that you get to before you fall back to the ground. Okay? So let's look at that. There's lots of ways you could do this, but the easiest way is to go from here to here as our initial and final, because then the Werk done between those 2 points is going to be 0 because it's a frictionless track. Well, at B, I have two kinds of energy. I have 1/2 m times VB squared, and I have mgh at B. But at C, it stopped moving. You got to stop to turn around and fall. And so at B, it only has gravitational energy. Now you see that all of these terms have an m in it, so I can cancel out the m. And if I divide both sides by g, what I get is that the height at C is equal to the height at B plus VB squared over 2G. And when I plug in the values for that, what I find is 17.2 meters. Now, the last part of this question just asks, well, what if we had launched this without any riders so that it wasn't 250 kilograms, it was less? Would you get higher with the cart, or would you get lower with the cart, or would it go the same height? And the key here is that whenever you're dealing with just kinetic and gravitational energy, the mass cancels out as long as there's no Werk being done. But when you deal with a spring, it throws everything off. Mass matters because the spring energy is completely independent of the mass of the cart. It just depends on the spring constant and how much you compress or stretch it, okay? And so that 60,000 joules that you start with is going to be 60,000 joules whether you start with riders or whether you start without riders. Well, let's talk about how much energy you lose to friction. Well, how much you lose to friction depends on how much normal force you have multiplied by your coefficient of friction. If you've got an empty cart, it doesn't weigh as much, your normal force isn't as big, and so you're not going to lose as much energy. So that means that when the cart ends up stopping up here, it's going to have more energy more gravitational potential energy than it did when they had riders, because you didn't lose as much here. Now, if I have more gravitational potential energy, even if I had the same mass, that means I'd go higher. But in this case, I have less mass. So I'm going higher for two reasons. First, I've got more potential energy at the end of my ride, if you call this the end, probably the last part you remember. And two, with less mass, that extra energy is even going to give me a higher lift height. So essentially, MGH is now going to be bigger. All of this is bigger. And since M is getting smaller, H has to even get bigger. I'm not sure if that made it clear, but I hope you see what I mean. Okay, again, this has been the homework set number 26, the homework that's due on Monday, the 6th of April.